Okay, so one thing that I said functional dependencies were useful for was talking about redundancy of schemas, redundancy inherent in schemas, and in particular for transforming schemas to make sure they didn't have that kind of redundancy. So the process of doing that is called normalisation. Now, there are various flavours of normalisation. In this video, we're going to talk about normalising towards a BCNF version of the schema. So we've got to start with a schema. So let's say we've got a schema S which has a whole bunch of attributes. And here, remember that initially when I was talking about functional dependencies, I said you could come up with an algorithm to derive a schema from a set of attributes. So here, we're just going to start with a set of attributes. So it's kind of like we got a single table. And what the normalisation is going to do, it's going to look at this, and let's imagine that we've got talking about a set of tables, which is what a schema would be. There's our single table. Is that table in BCNF? And of course, that's all relative to a set of functional dependencies. If it's not, then we're going to have to do something to transform it towards being in BCNF form. And as I mentioned earlier, that normally involves some kind of decomposition process. So we might ultimately derive a new version of S that involves two tables, A, B, and C, and C, D, and E. Now, one thing that's always going to be the case in these scenarios is that we have to have some kind of linkage between the tables that we generate. Otherwise, if we don't, we can't reconstruct the original data set. And of course, it's supposed to be the same database, just represented without any redundancy. So we must be able to reconstruct the original schema. That notion is called lossless decomposition. So here we started with a schema with a single table in, a set of functional dependencies. We decided that this table wasn't in BCNF, so we broke the schema into two separate tables, and if each of these tables is in BCNF, then we're done. We've created a BCNF schema. So that's how we can decompose a schema, a very simple example. So can you express that algorithmically? And yes, you can. So if we start and assume that our result schema, so we'll call that res, is our original schema. So the original schema S that we're given happens to already be in BCNF. The other thing that we have to be given, of course, is the set of functional dependencies. So somehow that's applied. So the inputs to this algorithm are this original schema, which is basically a set of all the attributes, and a set of functional dependencies on all of those attributes. All right, well, a schema is in BCNF if all of the tables in the schema are in BCNF themselves. So clearly our termination condition, or conversely our continuation condition, so while any of the tables, let's call the tables R for relation, any R in S is not BCNF. It means we've got some more work to do. So we have to do some kind of decomposition. Now, a lot of these decomposition algorithms, in fact, I think all of them, are non-deterministic, and at some point you have to make a choice. So here we choose some functional dependency from our set F that causes some table in the schema to not be in BCNF. So I guess we could write that. Choose an xy that causes BCNF to be violated. So technically it's not the functional dependency that violates the BCNF property, but it's the combination of the functional dependency and one of the tables. All right, so what we do is we then try to stop this thing causing a problem. So if we can take this functional dependency out of the original table and add a new table into the system, let's call it R prime. And all we put in R prime are these two things. Now, if we've simply got these two attributes and we stick them in the table, by definition, that table has to be in BCNF. So you might say, hey, we're going to end up with a bunch of two attribute tables. The thing about all of this discussion is, in fact, these capital letters here are really meant to be sets of attributes, but often we kind of treat them as being single attributes. So in any case, we end up with a table, a new table, which is more likely than before to be in BCNF. In fact, it's guaranteed to be in BCNF because the BCNF property is that for a given table and a given functional dependencies, all of the attributes on the left-hand side of the functional dependency form part of the key, and that's kind of by definition what's happening here. Now, that's fine in itself. That's adding an extra table to the schema, but we've still got our original table R. That's a problem. The way we can fix the problem is to take Y out of that table. So if we, with our squeaky pen, to remove Y. So if we remove Y from R, well, this functional dependency isn't causing a problem with R anymore. And so we're moving closer towards, well, it's not causing a BCNF problem with R. The other thing that I should have mentioned is we have to worry about whether FDs are relevant to a given schema. So in this case, if we take Y out of R, then Y still contains X, that's fine, but it doesn't contain Y, and therefore this functional dependency is irrelevant to that new table. So we are only interested in functional dependencies that contain attributes, all of which are in a given table. So that algorithm there will actually allow us to convert any schema with a given set of functional dependencies into BCNF form. Another thing to notice here is that we never change the set of functional dependencies, but we do start to ignore some if they're not relevant to the decomposed versions of the tables that we've produced. Okay, so let's take a look at an example. So I've been a little bit loose in this discussion here, and basically a schema or relation R isn't in BCNF if there's some functional dependency that doesn't have a complete key on the left-hand side. So that's the property that we're using to determine whether R is not in BCNF. So let's start with a schema that initially has a single table in it. You see. Where do we get these functional dependencies from? Well, interesting question, and I probably should have done an example of that earlier, but basically you look at the semantics of the table. In fact, we did do an example of that earlier, where we saw that the set of attributes, movie and year that it was made, functionally determined the other thing. So it's your understanding of the semantics of the problem that allows you to work out what the functional dependencies are. Now, of course, in database courses, we simply give you functional dependencies in a form like this, and you are meant to work from there. All right, so our initial schema, single table of 5 attributes, and this set of functional dependencies. So first thing we need to work out is what's the key of this table. Well, AB determines CD, C determines DE, and D determines F. So it's pretty clear straight away. You can see that AB is the key. So, and the way you can work that out is you take the closure of attributes under AB, and it includes all the attributes in the table. So AB is a key. All right, now we've got a single table and a key here, and it's clear that there are some functional dependencies that don't involve all of the key on the left-hand side. And an obvious one is this one, which doesn't involve any part of the key on the left-hand side. So that's the one we're going to choose. So the XY that we choose is D functionally determines F. And the goal here, remember, all the time, is that we're trying to make this schema closer to BCNF. So if we make this choice, then what we have to do, and I'll keep, rather than having R prime or whatever, I'll just keep, in fact, this thing that we've got here, we can always call the result schema. So, oh, I left out F. All right, so we had an attribute F there as well. It's a bit messy, but I'm about to rub it out, so it doesn't matter. Okay, so we've chosen D to F. So according to our algorithm over here, we make a table that a new table that contains DF, and we remove F from this original schema, or this original giant table, if you like. So we still have D, we still have E, but now we have a new table, DF. Now it should be patently clear from the definition I said of BCNF before that this table has only a key on the left-hand side of all of the relevant functional dependencies. That functional dependency is not relevant because it contains attributes C and E, which aren't part of this table. All right, so we can continue, go around the loop again. Oh, change R to remove Y. I've done that as well. So, all right. So, oh, I shouldn't have rubbed out the key because this key is actually still in play. AB. Okay, so AB determines CD, C determines DE. That determines all of the attributes. So that is still the key. Find another functional dependency. Well, let's have a look at this one. This has an attribute which also isn't part of the key. So therefore, this functional dependency and this schema aren't in BCNF. So we're going to choose the dependency C goes to DE. All right, so part of the deal is, given that dependency, we make a table that contains just those attributes. And then we remove these two attributes from this table here. Okay, So round the loop again. Let's see if we can find a relation in the current schema that isn't in BCNF. Now, ABC, remember that we can rewrite this dependency, and we could rewrite it as AB determines C, AB determines D. If we do that, this dependency is relevant to this table. It's the only dependency that's relevant to that table, and therefore, if we want to start giving things ticks, we already knew that was in BCNF. Now this is in BCNF, and the dependency that's relevant to this, well, that's the one that we used to create the table in the first place. The key is clearly C, and that's the only dependency that's relevant, and therefore that's also in BCNF. So this gives us the BCNF decomposition of our original schema under this set of functional dependencies. So in this case it was a relatively simple decomposition. There are more complicated decompositions that you'll find in the exercises and in the other videos.